Welcome, physics people. In this video today, we're looking at Faraday's Law, focusing on induced EMF. It was in 1831 that Michael Faraday first discovered electromagnetic induction, and here's the apparatus, his induction ring. Quite simply, the induction ring consists of an iron core, a copper coil on one side of the iron core, which is insulated with material, and a second copper coil on the other side of the iron core, which is also insulated. Here's the equipment that was set up. So we have a battery and a switch, which has been connected to one of the copper coils, which wound around one half of the iron core. The switch was toggled, and the galvanometer, which was connected to the second coil, was observed. So we're trying to find out, when we alter the position of our switch, what happens to the galvanometer? Does it detect current? Now, a galvanometer is a very sensitive microammeter. Scenario 1, when we open the switch. So the switch is open, no current flows through the first coil. Observation: with the switch open, Faraday observed no deflection of the galvanometer. No surprises there. Scenario 2, when the switch is closing, when it first closes, when the switch is initially closed, current flows through the first coil. In doing so, it creates a magnetic field. Observation: when the switch is initially closed, Faraday observed a brief deflection of the galvanometer. Therefore, a current had been induced in the second coil. It's moved from a vertical position to the right. Scenario 3, when the switch remains closed permanently. When the switch is closed, current flows through the first coil, as we see. Surprisingly, with the switch closed, Faraday observed the galvanometer return to its original position. No induced current in the second coil. Scenario 4, when the switch is opening, when we first open it. The switch is initially opened, current stops flowing through the first coil. So the switch is open, there's no current through this first coil. The observation: with the switch initially opened, Faraday observed a brief deflection of the galvanometer in the reverse direction. Therefore, there's an induced current in the second coil, traveling in the opposite direction. Finally, when the switch is left open, the switch is open, we have no current flowing through the first coil. Faraday observed, with the switch open, no deflection of the galvanometer whatsoever. So let's look at that in a summary. First scenario: open switch, no current in coil 1, no current in coil 2, therefore no deflection on the galvanometer. When we first close the switch, there is a current in coil 1, a current in coil 2, and therefore the galvanometer deflects to the right in this example. When we leave this switch closed, there's no current in coil 1, no current is found in coil 2, and no galvanometer deflection accordingly. When we first open a switch, when it's being opened, we find there's no current in coil 1. There is a current in coil 2 as the galvanometers deflect to the left. It's in the reverse direction to when it was being closed. And if we leave that switch permanently open, there's no current in coil 1 and no current detected in coil 2 as there's no galvanometer deflection. Let's look at this in a little bit more detail. In our first scenario, where we've got no current on either side, we have no change in magnetic flux, and that is why there is no induced current in the second coil. When we first close this switch, we introduce a magnetic field that runs around in a circular manner, and this introduces a change in magnetic flux. When we have a change in magnetic flux, that's when an induced current is created, and this is to the right. When the switch is closed permanently, we still have a magnetic field B, but it's constant, so there is no change in magnetic flux, therefore no induced current is detected in the secondary coil. When we then open the switch, even though we open the switch and we are removing the current in the coil, we find we have still a change in magnetic field. Okay, it was all the way around, it is being reduced to 0, and therefore an induced current in the secondary coil to the left on the galvanometer. And finally, when we have no current in coil 1 with an open switch, that means we have no magnetic field, and so there is no change in flux, therefore no induced current in the second coil or deflection of the galvanometer. Faraday's findings. Faraday found it is the changing magnetic flux over time relative to the coil that induces a current or electromotive force, an EMF. Let's look at his law. It looks quite complex. It states that the EMF is equal to the negative number of turns in a coil multiplied by the rate of change of magnetic flux per time, or phi dt, where E is the electromotive force in volts, N is the number of turns of the coil, delta phi is the change in magnetic flux measured in Weber, and delta T is the change of time in seconds. We'll use that equation considerably to work out the average EMF within coils and magnetic fields. Also, we have a second equation which we should know from our background knowledge, that magnetic flux is the product of the magnetic field strength times the area. Now this little symbol says it's the magnetic field that is perpendicular to the area. Okay, where phi, B, is the magnetic flux in Weber, B is the magnetic field strength in Tesla, and A is the cross-sectional area in meters squared. The diagrams to the bottom right give a good graphical representation of magnetic flux. In our first diagram here, we find we have a magnetic field that is threading through the loop, which is perpendicular in cross-sectional area to the direction of the magnetic field. This generates a maximum magnetic flux. However, what we have here is the magnetic field, vector B, is parallel to the cross-sectional area. None of those lines are threading through the coil as they were in this situation, and so this generates, and there's our little parallel symbol, this generates 0 Weber. Just identifying the times and the situations where we have a maximum flux and 0 flux. For further information regarding Faraday's law, please check the following online simulators. We have the FET Colorado simulator, the Walter Fent simulator, and the National Maglev simulator. Looking now at the FET simulator, we've got a range of different options from our tabs up the top. You can see here that if we introduce a magnetic field into a coil, that will generate a current momentarily. If we hold it stationary, nothing happens. There's no change in flux. As we move it out, we find there's a change in flux and the current runs in the reverse direction, one way, then the other. We can also look at a generator. Generator is continually changing the magnetic flux. So if we were to run this scenario, what we find is we have a north field, which makes current go in one direction. Then we have an introduction of a south, which makes the current go in the other. The quicker we change the rate of flux, the greater the EMF or the voltage coming out of our circuit. Okay, again, we reduce the rate of magnetic flux change, the divided T, and we get a lower voltage coming out. The Walter Fent simulator here represents an AC generator. So unlike a motor where we use current to generate force, here we're using a force to move the coil in the presence of a magnetic field to generate an induced current. This is a really good simulator to have a look at what effect the orientation of our coil has upon the polarity of the output. You can see here that current is moving inwards, then it switches outwards, and so we continually change from an AC that's positive to an AC that's a negative amplitude, and that's seen by this cosine type relation. Maglev have a nice simple demonstration indicating how electromagnetic induction works. So we have here, the apparatus is a coil hooked up to a voltmeter. We have a small magnet, and we're going to introduce that into the coil, thereby changing the magnetic flux and inducing a current in one direction. So if we watch the dial of our voltmeter, you'll see it momentarily pulses to the right. Now the magnet is inside the coil, stationary. There is no change in flux. There is a magnetic field, but there is no change in flux, so we get no EMF coming out. Now we'll remove it and we'll watch the needle deflection on the voltmeter. Again, change in flux as I remove it, and the voltmeter went to the left. So if we watch this again, north in, pulse to the right, north out, pulse to the left. We can increase the number of turns on our coil. As we know from Faraday's law, the number of turns does multiply the EMF generated. So with greater turns, as we move this in, we should find we get a greater EMF as we move it to the right and then move it to the left. Well worth a look at. This is the Maglev. Question 1. The alternator shown below has a rectangular coil with sides of 0.3 of a meter and 0.4 of a meter and consists of 10 turns. The coil rotates 4 times a second in a uniform magnetic field. The magnetic flux through the coil in the position shown is 0.20 Weber. So here's our diagram. We've got a set of slip rings going into our alternator, and we've got magnetic fields in our coil here. So part A, calculate the magnitude of the magnetic field. Include appropriate units. So we want to find B, the magnetic field. The area we have is 0.3 by 0.4 of a meter. If I multiply those two together, I end up with a cross-sectional area of 0.12 meters squared. And finally, we're given the flux. The magnetic flux through the coil is 0.20 of a Weber. The equation that relates these variables is the magnetic flux is equal to the magnetic field strength times the cross-sectional area. So I can rearrange that and work out the magnetic field strength is equal to the flux divided by the cross-sectional area. Flux is 0.20 over Weber, area is 0.12 of a meter squared. So that gives me a magnetic field strength of 1.67 Tesla. Part B, calculate the magnitude of the average EMF generated in a quarter of a turn. Show all the steps of your working. So first of all, the EMF is our unknown, that's our question. There are 10 turns in this coil. Now the change in flux is our final magnetic flux, take away our initial magnetic flux. So first of all, in a quarter rotation, we start in a vertical position here where the flux and the cross-sectional area are perpendicular. Our final arrangement, a quarter of a rotation later, 90-degree rotation, will be where our magnetic field and our cross-sectional area are parallel. That generates 0 magnetic flux. So our final value was 0 Weber. Our initial value in this arrangement is a cross-sectional area that is perpendicular to the magnetic field lines threading through it. And we were told earlier that that had a flux of 0.20 Weber. So our initial value was 0.02 of a Weber. So that gives me a change in flux of minus 0.20 Weber. Our change in time is a quarter of the total rotation, the total period, because we're analyzing a quarter of a turn. So let's look at our overall period for one complete rotation. It's 1 over the frequency. It's the reciprocal of the frequency. And it rotates 4 times a second. That means if something is rotating 4 times a second, the period it takes for one rotation will be 1 over 4. So the period for a full rotation is 0.25 of a second. Now we're after the time it takes for a 1/4 rotation. So it's 1/4 of the total 0.25, which gives me a delta T of 0.0625 seconds. So here's our equation to work out the EMF. So the negative goes in, number of turns is 10, the change in flux was minus 0.2, and the delta T for a quarter rotation was 0.0625 of a second. Multiply those together, that works out an average EMF of 32 volts. Question 2. A square loop of wire of 10 turns with a cross-sectional area of 1.6 by 10 to the negative 3 meters squared passes at a constant speed into, through, and out of a magnetic field of magnitude 2 by 10 to the negative 2 Tesla, as shown below. So you can see as it moves in between the magnetic fields, this is a side-on view. From above, we see our coil is going up to and then into our magnetic field from position X into position Y. Magnetic field lines go from north to south, so from above that represents the crosses going into the page. The loop takes 0.5 of a second to go from position X to position Y, so from fully out of the field into fully into the field. And the question is, calculate the average EMF induced in the loop as it passes from just outside position X, the magnetic field, to just inside the magnetic field at position Y. There's a bit of information here, so let's go through this. So first of all, the EMF is question. Area is 1.6 by 10 to the negative 3 meters squared in the correct units. Quite often they might be centimeters squared. Be careful of that. The magnetic field is 2.0 by 10 to the negative 2 Tesla. That's the uniform magnetic field between the two poles. The flux when it's at position X, outside of the magnetic field, is 0 Weber. The flux at position Y. This is now a scenario where the coil is fully in, its cross-sectional area is perpendicular to the magnetic field, so it's going to be the field strength multiplied by the cross-sectional area, and it comes out to 3.2 by 10 to the negative 5 Weber. So there's our flux at X and our flux at Y. Subtracting the two to find our change in flux gives us a value of 3.2 by 10 to the negative 5 Weber. So there's our change in flux. Our time that it takes to move from position X to position Y is 0.5 of a second, half a second. And of course we've got 10 turns in this coil. Our equation for the EMF equals negative N, change of flux over the change in time. So negative 10 times 3.2 by 10 to the negative 5 over 0.5 gives me a value of negative 6.4 by 10 to the negative 4 volts. However, when we're calculating these EMFs, we're not worried about the sign, we're only after the magnitude. So that would be rewritten as 6.4 by 10 to the negative 4 volts. Question 3, a graphical question. The coil of an AC generator completes 50 revolutions per second. A graph of output voltage versus time for this generator is shown below. So here's our graph. Which of the following graphs best represents the output voltage if the rate of rotation is changed to 25 revolutions per second? So there's our original frequency of 50 Hertz, 50 events per second. And here's our change frequency, our second scenario, 25 Hertz. Now that represents half the original frequency. Now we recall that period is equal to the reciprocal of the frequency. So if the frequency has been halved, that means the time it takes the period will have been doubled. Okay, you're going to get half as many events in the same period of time, which means it will take twice as long to complete the event. So here's our original period from our original voltage traveling up from a zero position, comes back down, and then it repeats here. It starts to go up again. So that's the time it takes for a complete cycle period. So we're looking for an option here that has double that period. This one here is, it's only got half the period. That's no good. This option also has got half the original period, 1 unit across compared to 2. So that's impossible as well. So I've eliminated 2 options just by looking at the period. These 2 options, B and D, have both got double the period, so they're both possible. See, that's 1, 2 units across on the time axes. This is 1, 2, 3, 4. 1, 2, 3, 4. Option B and D are possible. Let's try and distinguish between these. Now, the EMF is proportional to the rate of change of the flux. Okay, how quickly we change our flux. So we know the change in period for our change scenario will be double that of our original scenario. So a factor of 2. When I put in a factor of 2 on the bottom on my delta T, we find the EMF we get out of this will be only 1/2 the original EMF. So our value here, our original EMF, had a peak voltage of 1 volt. Voltage graph B still has a peak voltage of 1 volt when it's actually meant to be half of its original value. So that's no good. That leaves us with option D. It has got half the original peak voltage, so that is our correct option. Now this is quite simple. If we were to rotate a generator, a handheld generator, at only half the frequency, it would take twice as long, and thereby this fraction, to phi to t, will have a bigger denominator, which makes the overall fraction smaller. So the voltage coming out of a generator, when we're spinning at only half its speed, will be half the amplitude as well. So we can detect option D by the change in period, and also by the change in amplitude, the peak voltage. Finally, question 4. Students in a physics practical class investigate the piece of electrical equipment shown below. It consists of a single rectangular loop of wire that can be rotated within a uniform magnetic field. The loop has the dimensions of 0.5 of a meter by 0.25 of a meter and is connected to the output terminals with slip rings. The loop is in a uniform magnetic field of strength 0.40 Tesla. Part A. Which name best describes the piece of electrical equipment shown left? Is it A, an alternator, B, a DC generator, C, a DC motor, or D, an AC motor? First clue here. These wires are outputs. They're not inputting current, they're taking current away from the system. So current is an output. This is not a motor. A motor requires current going into the system in order to generate kinetic energy. So motor options are both ruled out. These 2 joins here are slip rings, not split rings. Slip rings are used for AC generation. So that will rule out the DC and leave us with AC as our option. An alternator is the same as an AC generator. Part B. What is the magnitude of the flux through the loop when it is in the position shown? So we know that flux is the product of the magnetic field strength multiplied by the area. In this situation, the magnetic field is parallel to the cross-sectional area. They're all in the same plane, so there is no flux. There is no flux threading through. No magnetic field lines thread the cross-sectional area of the loop, therefore no magnetic flux. So it is 0 Weber. The student connects the output terminals of the piece of electrical equipment to an oscilloscope. One student rotates the loop at a constant rate of 20 revolutions per second. Part C is to calculate the period of the rotation of the loop. So the period is question mark T. Frequency F is 20 Hertz, 20 events per second. And we know the period is the reciprocal 1 on F. So 1 on 20 gives me a period of 0.05. So this apparatus would take 0.05 to do 1 complete rotation back to its starting position. Part D, calculate the maximum flux through the loop. Phi B, the magnetic flux maximum, equals question mark. The area is 0.5 by 0.25, both in meters, which gives me a cross-sectional area of 0.125 meters squared. And the magnetic field strength is 0.4 of a Tesla. Maximum magnetic flux occurs when the surface area of the coil is perpendicular to the magnetic field strength. So 0.4 times 0.125 gives me a 0.05 Weber as our maximum flux. And part E, what is the average voltage measured across the output terminal for the first quarter turn? So the EMF equals question mark. And it's a single rectangular loop of wire, so N equals 1. Now the change in flux takes the final flux to take away the initial flux. If we go a quarter rotation, the final flux was that maximum value that we did earlier, ends up being 0.05 of a Weber. And the initial here, the initial flux was 0. So my change in flux will be 0.05 of a Weber. That's why we often choose a quarter rotation, because one of those values will always be a maximum and the other will be 0. So the change in flux will just equal the magnitude of the maximum flux. So the time it takes for delta t, a quarter rotation, will be 1/4 of the total period. And we discovered earlier the period was 0.05 of a second. So delta t for a quarter rotation will be 0.0125 of a second. EMF equals negative n multiplied by the rate of change of the flux, d phi dt. Substituting our values, n equals 1, change in flux was 0.05, and the change in time was 0.0125. That gives me an EMF of negative 4 volts. Again, we're normally after the magnitude only, not the sign. So the EMF in this situation is 4 volts. Part F. State 2 ways the amplitude of the voltage across the terminal can be increased. Well, here's our equation. Let's look at how can we increase the EMF. So first of all, the EMF is proportional to the number of turns. So we could increase the number of turns. That would give me a greater EMF. The EMF is proportional to the magnetic field strength. We could increase the magnetic field strength to get a greater EMF. That's 2 possibilities, but there's more. The magnetic field strength is proportional to the cross-sectional area. So we could increase that by making our loop larger. And the EMF is inversely proportional to delta t. So we could decrease delta t, the time of rotation. That will, decreasing the denominator, will increase the overall fraction and therefore give us a higher EMF. That effectively means to spin the coil faster, okay, which is really increasing the frequency of the rotation. Any 2 of those scenarios would result in a larger or an increased EMF. Thank you so much for watching this video. I hope it's explained some of the concepts of Faraday's Law and also the relevant equations with calculations from past VCAA exams. If you enjoyed this, please like, share, comment, and subscribe. And as always, thanks for watching.